Hello there, Algebra 2. This lesson is going to be covering 7.2, the graphing of rational functions, so something a little bit new. Hope the matrix unit went well for you. This one, we have a couple more lessons left, and then that's it for the completion of this cycle right now. So a rational function is what the next three we're going to be looking at, and it's going to be several review topics that are coming up again, a little bit new and a lot of review. Okay. So again, a rational function, this fits in a function like linear functions and quadratic functions, absolute value functions. It's another type of function. It's another family of function. Okay? The parent function for a rational function with a linear numerator and a linear denominator. So what we're going to see right here is no x squares. We're not going to see any rational function that has an x squared in it. We're just going to be looking at linear ones. In the coming lessons, those will start showing up, but we won't be looking at the graph so much. Okay, so this is our parent function, 1 over x, and this is what it looks like right over here. These right here, the whole graph is called a parabola. Okay, this part, each individual part, those are called the branches. Okay, it's kind of like a tree. You have two parts to this graph. Okay, in this case, if this is a positive value on top, you're going to have graphs in the first and third quadrant. Remember, the quadrants go 1, 2, 3, 4. Okay, 1, 2, 3, 4. They're your quadrants. So these branches right here, as you go forever to the right, it's going to get closer and closer to the x-axis, but it's never going to touch it. So imagine putting really large numbers down here. Okay. If you go 1 over 10, that's 0.1. 1 over 1,000 would be 0.001. So this number is just getting really big, 1 over a million. 0.1, 2, 3, 4, 5, 1. Okay? So no matter how large this denominator gets, this number is just going to get closer and closer to 0. Okay? Same thing happens on the left side. As you get really large negative numbers, it's going to get closer and closer to 0. So if this is 0 right here, this would be the top. If you have a positive x, you're getting closer and closer from this way. If you have a negative x, you're getting closer and closer from this way. Okay? Or if you're on the number line, positive x's, you're getting closer and closer here. Negative x's, closer and closer here. Kind of the inverse happens along the y-axis. As you get really small x numbers, your y value, 1 divided by that, is going to get really large. So if you take 1 divided by 0.00001, that would be 100,000. Okay? So again, as this gets closer and closer to 0, this number gets really huge. And that's what's happening here. But it's never going to be 0. Okay? Because it's 1 over the number. It's never going to be 0. So from that, we can get our domain. This is the domain for the parent function, that x cannot equal 0. Okay? So x can be anything, but it can't equal 0 for the parent function. And our range, because we're never, when we have 0 here, we don't have a y value. Okay? And our range is y cannot equal 0. Now the last thing with this little graph here is we have a fancy name called an asymptote. Okay? Asymptotes in this case are going to be the y-axis and the x-axis. Okay? And an asymptote is a name that refers to a line that a graph gets closer and closer to, but it never actually touches. Okay? I don't remember right now if we've talked about that before. But this is what the x-axis is right here. It's an asymptote because this graph will get closer and closer and closer to, but it never actually touches or contacts it. Same thing with the y-axis. So these asymptotes are huge in recognizing the graphs of these. And if you can recognize the graphs on this assignment, you actually don't have to graph anything. There's going to be, I know it's called graphing rational functions. We know online a lot of this is multiple choice. I want you to be able to recognize where should these asymptotes be and which graph is it based off of that information. Okay, so reviewing here a little bit graph transformations. Now, any adjustment in the denominator, okay, remember that is going to be a horizontal shift. So the asymptote, this is page 195, occurs wherever the denominator equals 0. Wherever the denominator equals 0. So I have 1 over x minus 1. So x minus 1 equals 0, x minus 1 equals 0 when x equals equal to 1. What that means is we have a vertical asymptote at x equals 1. A vertical asymptote at x equals 1. That's what we have here. The y-axis is x equals 0. X equals 0. That's a vertical asymptote. So wherever this equals 0, wherever the denominator equals 0, you're going to have a vertical asymptote for right now. Okay. So when you look at your graph, you're like, okay, well this is at -1. This one is at +1. The others on this side. This one is at +1. This one's at -2. This one's at +1. And this one's at -2. So we have three options here. We have C, E, and B that are going to be our selections for A. Now notice this is positive. So when this is positive, it's going to match our parent function and have graphs in the first and third quadrant. So that takes out option B. Our graph should be over in the first quadrant and third quadrant, okay, not in that direction. So it can't be B. We have C and we have E. Now notice with E, see this line here, this is a new line. And it's actually up here at 1. This is a horizontal asymptote. So the horizontal asymptote comes from the top. So we're going to get our vertical asymptote from the bottom. And if the top is a constant, horizontal HA, horizontal asymptote, would be y equals 0. It's going to look like our parent function here. So horizontal asymptote y equals 0, that's going to put our graph as option C. Okay. So we have a horizontal shift, 1 unit right. We don't have any sort of vertical shift. Okay. Horizontal shift, but not vertical shift. So graph A would be, or equation A would go to graph C. Okay. So what's different when we go to B? We still have a vertical asymptote that comes from the bottom at x equals 1. The top is a constant, so we have a horizontal asymptote at y equals 0. So you notice how this looks exactly like equation A, except now we have a negative number in front. The negative number puts it in quadrants 2 and 4. Quadrants 2 and 4, and that's going to be graph B that we saw earlier. So we have vertical asymptote at x equals 1. We have a horizontal asymptote at y equals 0. So it's been shifted 1 unit right, but not up and down. So this would be graph B. Okay? So equation B goes to graph B. Okay. C, D, E, and F. You notice now that we have variables on top as well. Okay, A and B, we just had a constant up there, which makes things easier. When we start getting variables on top, we start adjusting the graph up and down as well. Okay? Now, still, your vertical asymptote is going to come from the bottom. So we have a vertical asymptote, VA. Where does x minus 1 equal 0? Well, that would be at x equals 1. So I have a vertical asymptote at x equals 1. So we still have all those options. We should know by now it's going to be our third one, because it's the only other one that has a vertical asymptote at x equals 1. But how do you get this the horizontal asymptote, which in this case is y equals 1? It's not y equals 0 like it was up in graph C. It's y equals 1. So when you have x's in front, you want to look your horizontal asymptote equals the ratio of the leading coefficients. Oops, ran right off that page. Ratio of the leading coefficients. Well, remember, the leading coefficients are the numbers in front of the variables. So I have a 1 here and I have a 1 here. So my horizontal asymptote would be y equals 1 over 1, which is 1. Y equals 1. There's that y equals 1. Okay, we're going to talk a little bit more about the proper way to do this, but it's always going to just be this ratio right here of whatever's in front of x. Okay? So let's look at this one. I look at my bottom. I have a vertical asymptote at x equals -1. Now I look at my top. I see I have an x and an x. So I have a horizontal asymptote at y equals, I look at my ratio, 1 over 1. At y equals 1 over 1, which is 1. So again, this one has a vertical asymptote at x equals -1. A horizontal asymptote at y equals 1. Vertical asymptotes are vertical lines. Okay, horizontal asymptotes are horizontal lines, so don't get those confused. So right here on A, I have a vertical asymptote at x equals -1. There's -1. And a horizontal asymptote at y equals 1. So y equals 1. But notice the branches are in the second and fourth quadrants. So that means there should be a negative somewhere turning things around. That negative in front of the 2 doesn't count. Okay. So I keep looking. This one has a vertical asymptote at x equals -2. That one would be it. They have this wrong. That's the only one with x equals -1. Did they do something wrong? I didn't look over. There's x equals -2. That equals x equals -2. You see the two -2's there, so this is the only one that's left. Hope I didn't do anything wrong. Let's check this while we're here. X minus 2 divided by x. Oh, it did switch it around. Oh, I'm sorry. We may have to go through the long haul on some of these. Okay, this -2 turns these things negative because this number is going to be smaller than this number. Okay, that negative there did flip it around. Okay, thank you, Desmos. So this one would be A. Okay, didn't catch that. So the proper way to do this, let's hit that, is actually the long division. This is where we get to review long division. Okay, so if I take x plus 1 and I'm dividing it into x minus 2. Okay, so we get to review this. X plus 1, the bottom goes on the outside, x minus 2 goes on the inside. So I take the inside over the outside. So if I take x over x, I get 1. That's going to go up here. I take that times my divisor coming down, x plus 1. You may need to find those notes, pull them out again. And I get x plus 1. So now I subtract by changing my sign. So that's a minus, that's a minus. So those should always cancel off. -2 minus 1 is -3. This is our remainder, and our answer is written as 1 minus 3 over x plus 1. Okay, so there's the minus sign that shows up if we're going to do this correctly. So maybe I thought we could have a shortcut with this, but maybe we do need to do this way. Okay. A lot of times, if you'll go off these asymptotes, you'll be able to figure it out. Which one? Okay. The 1 minus. So there's the minus that tells you you're in the second and fourth quadrants. Okay? So the 1 right here, we're going to see this in a little bit, that is this whole number that shows up, that represents your horizontal asymptote. Y equals 1. And again, from down here, you get your vertical asymptote, x equals -1. Okay? So on these next two, again, if you don't have plus or minus on the top, I would just look at what we've been seeing here. You should have a vertical asymptote from the bottom at x equals -2. You have 1 over 1, so you should have a horizontal asymptote at y equals 1 over 1, which is 1. So that one should be graph D. -2. Throw me for a loop now. Let's check it. So x plus 2, this is E, going into x plus 0. So x over x is 1. 1 times x plus 2 is going to be x plus 2. Huh, it does. I'll be honest, I'm learning a little something here too. It's been a while. So change my signs, I get -2. So I get 1 minus 2 over x plus 2. So that minus right there does tell you the graphs are in the other two quadrants. Looks like we'll have to do that. I thought I had a shortcut for you. So that should be F. Okay, -x over x plus 2. Now that should be D. Okay, notice that -x, but then the branches are in quadrants 1 and 3, like it should be a positive. So let's check that out. If I take x plus 2 into -x plus 2, nope, -x plus 0, Remember, you have to fill every position when you're dividing these. So if I take -x over x, inside over outside, I get -1. So I get -1 times x plus 2, that would be -x minus 2. Change your signs. First one should cancel off, and you get 2. So it's -1 plus 2 over x plus 2. So the -1 is your horizontal asymptote, y equals -1, and then you have -2 as your vertical asymptote, and your quadrant should be in the first and third. Okay, let's keep going here. So, kind of a review, determine the intercepts, asymptotes, domain, and range of the rational function here. So the intercepts, remember, for a y-intercept, you're going to plug in 0. And evaluate. So if I put 0 here, I get a over b. So g of 0 would equal 0 minus a over 0 minus b, which is a over b. So that would be your y-intercept. For an x-intercept, what you do with a rational function, you're going to set the numerator, which is the top, equal to 0, and solve. Set the numerator. So I'm going to set x minus a equals 0, and I get x equals a. So my x-intercept would be at a comma 0. My y-intercept would be at 0 comma a over b in this case. Okay. Asymptotes we've already talked about. Domain and range we've already talked about. Okay. So here's kind of the summary of what we have. The graph here, 1 over x, it's called a hyperbola. Consists of two symmetrical, they are symmetrical parts called branches. There's your branches. The domain and range are all non-zero real numbers, everything but 0. Okay, any function of the form a over x, where a is not 0, has the same asymptotes, domain, and range as your parent function. Okay, and those are the first ones we're going to look at. Okay, here's your general formula. So to graph a rational function of the form y equals a over x minus h plus k, draw the asymptotes x equals h, so that's where the denominator equals 0, and y equals k. So again, that tells you your horizontal asymptote, and this tells you your vertical asymptote. Okay, x equals h is a vertical line, y equals k is a horizontal line. Plot points to the left and right. There, I want you to actually plug in numbers to do it, and then draw the two branches. All right, so let's get some practice here, page 198. We're not going to be concerned about finding too many points. We just want to get our asymptotes correct and then get the graph drawn. Okay. Compare with the graph 1 over x. We'll talk about that. So we have 0.25 over x. So I'm going to draw my x and y axes. Okay. Notice my vertical asymptote is x equals 0. My horizontal asymptote is y equals 0, because this is just basically the parent function. Okay? So when x is 1, I get 0.25. And I know my graph is going to be basically going through here. The smaller that number up there, the smaller that number, the tighter this graph is going to be to there. If I have 1 over x, it's just going to go through 1, 1. It's going to come down, hit that point, go through there, or negative 1, negative 1. Since I have a 0.25 in there, I'm going to hit 0.25s on both those spots. If I had a 2 on top, I would go 2, 1, and 2, 1, and 1, 2. Okay? So compare this to kind of tighter. Our domain is going to be x cannot equal 0. Our range, y cannot equal 0. There are no x or y intercepts in this case, because those are also the asymptotes, so no x or y intercepts. Okay. Y equals negative 2 over x. Notice the negative 2, that's going to change your branches into the second and fourth quadrants. Okay, all of this stays the same as well, so we can copy that over. Oop, there we go. Domain, range, everything, because it's a constant over a number. So negative 2, when x is 1, we get negative 2. When x is 2, we get negative 1. So there's kind of a couple points that you can try to graph from. You notice the number got bigger on the top, and so we got farther away from this intersection of the asymptotes. This was a smaller number on top, and we're closer. We're tighter curve in here. So the smaller the number on top, the tighter the curve. The larger the number, the bigger the curve. If I go negative 2, I'd get 1. If I go negative 1, I'd get 2. Okay? Those are the fun ones. Easy ones. Okay, these are already in intercept form. So I'm going to look down here. I have x minus 3, so I get x equals 3. There's my vertical asymptote. And right here is my horizontal asymptote. That should be an h. Y equals 5. So 3, 5 is kind of where they cross. I'm going to put my y-axis about right here. Maybe my x-axis right here. So this is my x-axis, this is my y-axis. What I'm going to do is I'm going to draw a dashed line at 1, 2, 3, and this is basically serving as my new axes. I'm going to treat it like an axis, but it's not the real axis. Okay, so there's my vertical asymptote, and 1, 2, 3, 4, 5. Okay, so if I kind of treat this like 0, 0, that tells me, okay, I have a 1 up there, just a 1, so 1, 1, and 1, 1. And it should follow those lines right there. Okay, so you're not going off the original x and y, you're going off your new ones, which are your vertical and horizontal asymptotes. Okay, this one, I notice there's no horizontal shift. I see a negative 3 up there, and then a minus 4. So I'm not shifting it horizontally, so I'm just going to put I have a vertical asymptote at x equals 0. I have a horizontal asymptote at y equals negative 4. I'm just going to put my vertical axis, my y-axis right in the middle, and then this one I'm going to put a little bit higher. Because I know I have to shift my graph 4 units down. So 1, 2, 3, 4. And then it's negative 3 over x, so it should be in the second and fourth quadrants. So when x is 1 unit to the right, it's 3 down and 3. Notice I got farther away. There's 3 in there, expands it a little bit. Negative 1, 3, negative 3, 1. Now notice, I know those, what I'm saying there are not the specific x and y values. This point is actually negative 1, negative 1. This point is actually 1, 2, negative 3, negative 3. But from my new, if I treat this as kind of my origin, it'd just be 3 left and 1 up. Okay? Okay, rewrite the function in the form a over x minus h plus k, then graph the function. describe g as a transformation of your parent function. Oh, we need to state the domain and range here. Sorry, go back up here. Domain is going to be x cannot equal wherever the asymptote is, 3. So x cannot equal 3. The range, y cannot equal wherever that 5 is. So basically take these. This is going to be your domain except with the not equal sign. This is going to be your range but with a not equal sign. If you want interval notation, that'd be negative infinity to 3 union 3 to infinity. Negative infinity to 5 union 5 to infinity. So this one, your domain, x cannot equal 0, and your range, y cannot equal negative 4. Okay? So again, from here, that's your range, everything except that. Wherever your asymptotes are, they're not part of your range. Kick them out. So we have to use the long division here. I'm going to go x minus 5 going into x plus 2. So I take the inside over the outside, x over x, and that's a 1. So 1 times x minus 5 is x minus 5. Change your signs, and that cancels, and you get 7. So I have 1 plus 7 over x minus 5. So I have a vertical asymptote at x equals 5. I have a horizontal asymptote at y equals 1. I can get my domain and range right now as well. So x cannot equal 5, and my range, y cannot equal 1. So x equals 5. That means I probably need to put my x-axis farther to the left. My y-axis just down a little bit. So I can go up 1. So 1, 2, 3, 4, 5. Yeah, pretty close. Here's my new x. This is my vertical asymptote, and y equals 1. Okay, so this graph has been shifted 5 units right and 1 unit up from a over x. Okay, so this was a 7 over x. That means if I go over 1, 2, 3, 4, 5, 6, it's actually up here. 3, 4, 5, 6, 7. This is very stretched out hyperbola. We don't have a whole lot of room for. It is, okay, it is a positive, so, excuse me. 2, 3, 4, 5, 6, 7. Pardon me. 1, 2, 3, 4, 5, 6, 7. So that 7 really stretches that out. That's not a very good branch there, but you get the idea. Ooh, a big one. Look at this. You know what I do first on this one? I noticed that the top I can write as 2 times x plus 4. The bottom I can write as 3 times x minus 4. Interesting. I'm not sure if that's helpful, but I did notice that. Okay. So that means you should end up with a vertical asymptote at x equals 4, which means our domain is going to be x cannot equal 4. And we should end up with a horizontal asymptote of y equals 2/3, 2 over 3 right there. So your range should be y cannot equal 2/3. Okay, let's see if where these graphs end up going. So I'm going to go 3x minus 12. I'm taking that into 2x plus 8. So I'm going to take 2x over 3x, and I get 2/3. There's your horizontal asymptote, up 2/3. 2/3 times 3x minus 12 gives me 2/3 times 3 is 2, 2x. 2/3 times 12 is 8, so I get 2x minus 8. If I change my signs, I end up with a 16. So this graph would be 2/3 plus 16 over 3x minus 12. So that just tells you should be in the first and third quadrant. So I got a 4 and 2/3, so there's my x. There's my y. I'm going to go up to 2/3 approximately. Okay, you're just recognizing graphs a lot of this. 2, 3, 4 on the assignment. You won't actually have to draw it. Oh, that should have been dashed. Dash, 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 dash. So 16, your graphs, it's positive, so they should be in these two quadrants here. Okay, you get the general idea. Till it's the end of the lesson. Okay, so that hopefully takes care of all your graphing questions. Again, a lot of multiple choice. Try not to rely on Desmos with this, but use some of the characteristics and the asymptotes that we've talked about. Identifying the graph and selecting what they have and same with the parent function. Okay, this lies closer or lies farther away, that's dealing with the 1. Okay, if the number is larger than the 1, remember the graphs lie farther away from the axes. If this number that's on top is between 0 and 1, they're going to lie closer to the axes. Okay, state the domain and range, all numbers except blank. Range is all numbers except blank. Go off your asymptotes for that. Alright, here you may want to use the long division to check to see, just make sure where should your branches be. Should they be in the first and third or second and fourth? And that's it. A lot of recognizing the graphs, matching them up. Okay, try to do this looking at the equation and not just looking at Desmos, please. So, good luck. Let me know what questions you have. Go back there. And I'll see you soon. Bye.